Then precondition, the way how the preconditioner should be constructed. The two different ways to look at the preconditioning for eigenvalue problem. I wanted to take a few minutes to show the code that I put on web and point to the part of the code where you need to pay a little attention when you do the modification. So let me start running the code for steep descent and preconditioned steep descent, then you will notice the difference. So let's run, if I type input 1, that would be steep descent. It will show that. And this one that I showed before, it computed 4 eigenvalue with the deflation that we talked about. The first one seems good because it get residual about 10 to the minus 6, and still very slowly run up to 500 iterations. And then the few next, the second to the third to the fourth is very slow. Now let's look at the preconditioner one. So if I type if input 2, that would be preconditioner. And the first eigenvalue will take about 10 iterations to get to the 10 to the minus 13. And the rest of the second, third, fourth still take a lot of iterations, but much less, and you get better accuracy. So that's something, if you run, you will see that. Let's look at the code a little bit. What's about the conditioning? Preconditioning. So the code, so they call preconditioned steep descent. The last S stands for shift. G is generalized. S shift is shift deflation that we talk about. And in there, you have an option can set. So we talk about two different kind of preconditioning. One, so there's an option input. Then when you look at the driver routine, we'll see that. We'll take a look at that too. The first preconditioner is A minus a shift times B inverse. Okay. How do we implement this shift? The preconditioner. One is the most natural one by direct solver, which is usually you don't do that. We put it here just for comparison and see how it works. In practice, knowledge metric, you don't do that. You might do the option 2, which is the way the shifter that I pick in the code that we just run is small enough, is smaller than the smallest eigenvalue. So A minus sigma B, which is shift B, is positive definite. It's implemented by conjugate gradient, linear conjugate gradient. And the third option I haven't implemented yet. So there are places say to be implemented. You can do it later on your own, but I haven't done that. The second option is the second preconditioner we talk about. You do the incomplete LDL transformation on this A shifted A minus sigma B, and then you drop D. D is supposed to be plus minus 1 on the diagonal. The one would be using LL inverse, LL transpose inverse. That's what we talk about. And then the second one, remember we're doing compute the first eigenvalue, and we do the second one through a deflation. The deflation, what we do deflation is through a shift. So the matrix actually changed. In a sense, you start with A minus number B. Once you have, say, once we have the first eigenvalue, first K, for example, then we are actually work on we'll actually work on this matrix, and then if you do a shift, if that you replace that by a shift, you do a LDL decomposition supposed to on this whole thing rather than A minus sigma B. So once you have the first k eigenvalue, your shift matrix should be like that. Then how do you do an inverse of that, or by any means you do if basically A is replaced by A minus if this is replaced by LL transpose approximate decomposition, then this will be LL transpose plus that whole thing. So that's why one of the options say is LL prime plus shift B times U times B times U. Of course, B times U is computed outside, it's passed in. B is passed in. Now, let's look at the direct solver, then you will have some idea with deflation or when you compute first eigenvalue, there's no deflation. So this is a B times U, the second dimension that I picked up. So K of 0. If K0 is 0, that means we're computing the first eigenvalue. There's no deflation is done. So you're going to be work on this matrix in terms of preconditioning. But if K0 is positive, then you do have deflation. You work on this matrix, and in terms of a preconditioner, you will in the direct solver case, you will need to compute you would need to compute the inverse of that, and this is a low rank matrix. And the first part is supposed to already have LU decomposition in the direct solver case. Once you, well, the reason I talk about direct, if you have direct solver case, when you try to approximate, you do the similar thing. So if that means if I know LU of A minus sigma B, that means I know how to do A minus sigma B inverse, which equal to U inverse L inverse. Basically doing a, well, remember, even though we write this way, U inverse L inverse, you never done that. You always implement it through linear system solving, right? So with the matrix, C here, so suppose you know C inverse and plus a low rank, and now you want to invert it. How do you do that? Anybody have any idea? Triply, yes. That's a famous formula. That's exactly right. So you're going to use the Sherman-Morrison, what's the last name? Woodberg formula for the block case. If the one vector was Sherman-Morrison, but block case. That's exactly what did here. So if you look at K0 equals 0 here, there's not much special there. But when you look at K0 is bigger than 0, here you do see a Sherman-Morrison formula right here. Because a lot of information, here's a V with BU. When you implement it, because BU is already know, when you do a preconditioning, a lot of them are no, you don't really going to want to compute the inverse, as I said. But this part, you can pre-compute a lot of things. For example, K0 even is positive, but K0 is typically small. In this case, the example that I run for 4 eigenvalues, normally might have more. Then K0 at most as 3, right? So that's the reason that you look here that I actually compute the inverse of this at most a 3 by 3 matrix here. So that's so you first do CIV, which is C inverse V. V only a few columns. You pre-compute it. You save there. So CIV right here. U slash L slash and BU. The reason PP because permutation when you do a LU decomposition. Then T would be the inside identity plus shift plus then they actually inverted. And then I actually see the shift is eventually multiply the invert T because T is small, so you want to to save a little bit. If shifted times the whole matrix, it would be a larger multiplication. So shifted move to multiply this 3 by 3, most 3 by 3 matrix in the example that I run. Then CIV times that. So this CIVIT is a tall skinny metric going to be saved there. Later when you solving the preconditioning inside, let's see here, this is the beginning. Okay, when you get inside the loop while the error, which is a residual, bigger than the tolerance, and the iteration number less than, you set a number, so don't let it to run forever. You write the code before, sometimes you could have a bug or something, it won't converge, and then it takes forever, I'll never finish. What you can do, you just stop the machine. Here, just set it to the large numbers so that it will stop. So what you see here, then inside you need to solve a linear system, all right, of the residual on the right, that's the preconditioner, and using the pre-Sherman formula because we have the formula stated before, we have compute, so we need to compute C inverse R, so that's C inverse right R here, then you have update. Then look at before we have computed C inverse V and C inverse V and inverse T. So that's an implicit apply a Sherman formula by in order to save. So you don't have to compute the CIVIT every steps because you pre-computed before outside. This is for direct. Now then. One of the options called conjugate gradient. When you do conjugate gradient solver, you have 1 minus sigma b p equal to r. That's called C. If C positive definite, you just do that, right? Now, when you have the shift case, your matrix of multiplication will be A minus sigma b then plus the shift. Your conjugate gradient routine need to update for that. If you look at the code that I call linear CG, there's an option say if the updated if updated 0 means is C without that part, you just do CP equal R. If there's an update which is passed in as if the update equals 1, then it passes the V vector, which BU is called V in the code, and all it does, it will affect the matrix of vector multiplication, right? So your CG have to be accommodated that, all right? Whoops, all right. Now, if you look at this driver routine for test 2, it passes the shift. So here I pick shift, I know roughly the eigenvalue is, so I pick shift is -5 times 10 to the minus 2. So move the first few eigenvalue to larger than the eigenvalue that I will compute. And then preconditioner, the first type preconditioner I'm going to be used, and use option 2. Then so preconditioner 1 uses 2, which means use a conjugate gradient. And you see it run pretty good. And now what happened when you look at this root? The routine I say k equal 1 and 4. So the first k equal 1, you compute the smallest eigenvalue. In that case, the BU vector, which start with the which is empty, because I haven't computed any eigenvector yet. Now later, every iteration I done for k run from 4, then you update BU. So after k equal to 1, BU has a 1 vector that's going to be passed into the preconditioned steep descent routine, and internally you're going to do it will do a shift deflation, and it looks pretty well. You see the picture, right? Okay. You can you can change them. So for example, we can use preconditioner 2, which is the L. So which do incomplete LU decomposition, incomplete LDL, then through DOA. Then you're using the, let's look here, save, where the routine. Then then F2 is using preconditioner of that, which include the shift. And you can test if you say preconditioner 2 option 1 without shift, the second eigenvalue third is very poorly. I test that. I'll let you try that. But let me just show this second type preconditioner using the option 2, which means I include the shift when for the later eigenvalue. It runs pretty well. Yeah. Yeah, it's run basically similar behavior. Okay. Now, yesterday we mentioned that you could use a preconditioner for one eigenvalue. You can change it every iteration. In this code, I didn't make that fancy. I just pick the shift for every eigenvalue. I use one preconditioner. That's probably the reason you see it is the first eigenvalue has better conversion rate. You see the line is steeper. The second, third, fourth is slightly, longer, take longer. That's the reason that it is more effective. The one that I picked more effective for the first, and less effective for the rest. Okay, so now as the homework assignment that I passed to you, that I want you to modify this routine to make an extended version, which means that in the steep descent or preconditioned steep descent, each step you search a space. Search a space is the Krylov subspace of order 2. The current approximation with A minus rho, which is the current approximation of the eigenvalue, current approximation of eigenvector. You do such space is the Krylov subspace of order 2. Extended. You can see the difference. Well, a preconditioner means that you have k right there. Extended would be to the mth order precondition Krylov subspace. That's a preconditioner. You can set identity as well. That's a new preconditioner. Yeah. To see the difference, implement simply by change the subspace. Okay. All right. Now let me. Any questions? How many of you have downloaded the code and play with it? It might disappear from the website. Okay. All right. Let me. So today we're going to This is a shift idea. Today we're going to start from here. Block steep descent. The single vector version is we basically present all the idea. Now we just put into the block case. What's the difference of a block case? So far we talked about single vector. So you start with one vector. You compute, perform the optimization. The eigenvector keep getting closer and closer to the first eigenvalue and the first eigenvector, right? So the single eigenvector SD, including the steeper descent, including the preconditioner extended version, so that's called variations. You compute the first eigenvector, and with the deflation, for the second and third in that order, one vector at a time. The convergence can be slow. We look at the steep descent without preconditioning. It can be slow when this ratio is tiny. Okay, if the ratio close to 1 is faster. That's from the convergence theory. It is tiny usually when number 2 very close to number 1. When the first two eigenvalue is close, even worse is a multiple. Okay. When they close enough, and then you get this ratio tiny. This ratio if it's 0, basically you will see the approximation barely move, stay almost the same. Now, in practice, sometimes we need to not just the one eigenvalue. We may compute several at a time. That's when the so-called the block version appears. And when you take a linear algebra, numerical linear algebra, you start with the power method, one vector at a time. Then later you talk about called simultaneous iteration, or subspace iteration. This is basically some similar idea. So you can use a block version to compute several eigenvalues at one time. Then you will see the eigenvalue, sum of eigenvalue converge much faster. And another benefit that is now you're in Sherry's lecture, she talked about a lot about how do you speed up computation using BLAS 2 or BLAS 3 operations. Before was a matrix vector, that's BLAS 2. But if you use a block version, here, most of the time we involve in matrix times vector. Now, if you use a block, instead of one vector is several vectors packed together, most of the operation is done through matrix multiplication, except the second matrix is tall skinny, but still matrix. You can do that. That's so-called BLAS 3 operations. It's much more efficiently on today's computer architecture. All right, better rate of convergence for the small eigenvalue, in the sense that, say, in the one vector version, you compute first eigenvalue. Now, if you use a block version for two eigenvalue at the same time, you will see the first eigenvalue converge faster in the block 2 version than block 1 version. Okay. And like I mentioned that before, this improvement is extremely similar. The same principle in a sense that to the subspace iteration versus power iteration. Okay. All right. Now, what we call block SD. Block SD by name, that your initially is not just one vector. You initially have several vector, which here is called n of b. So you have n of b vectors. for example, 10, n b equal 10. So you start with, for example, could be n by 10, 10 vector together. And there have to be full ranked. We know the eigenvector together is linearly independent. So there's make no sense to a low rank. The rank is less than the number of columns. So now we can assume this initially the jth column approximate uj, the jth eigenvector. At least we can assume the column space of x0 approximate the invariant subspace spanned by first and b eigenvectors, right? That's reasonable. You can, if not, you can always do pre-processing. You can always project A and B, do a one eigen decomposition of the project matrix, which is smaller, and then you reset the initial vector. Then once you've done that, each column going to be approximate to the corresponding eigenvectors. All right. So because of that, you can always assume initially each column of x0 is approximating a particular eigenvector. All right. Now let's look at the typical steps. In the SD case, the typical step is find the best possible approximation within this Krylov subspace of order 2. Now you would have X has NB columns. Okay. Now how do you expand them space? In this case, in the SD case, this space, this is equal the span of two vectors, x and the residual, right? So that's the approximation, that's the corresponding residual. So now, because we're assuming we are making each, for example, xl1, the first column is approximating u1, and that will, the first vector will give rise a residual because of this as an approximation, all right? So each column going to introduce a residual. So xl1, from xl1 you can compute a residual xl1, and so on and so forth. And then in the end, you just put all those vectors together. How many vectors? 2 NB vectors. So you put all those vectors, the x vector and the residual vector together. You form a space of dimension, usually dimension of 2 times NB, and that will generate a subspace. But we need to now it's possible as the computation goes, sum of R is going to be almost 0. That's what you wanted, right? It's going to convert to 0. Otherwise, you wouldn't be doing that. So this, if you just put XLIR together, it's going to be yield condition because sum of going to be tiny. So what we're going to do, we're going to produce a B, usually B orthonormal basis of this space, okay, using modified Gram-Schmitz in B inner product, for example. So you produce subspace basis. That we call that matrix Z. Usually Z has 2 times NB columns, and then you project the matrix, project the original pencil. That will give you. This will be 2 NB times 2 NB metric pencil, but we're only interested in the first NB eigenvalues. So we could pick the smallest first half out, and this is a partial eigen decomposition. It's not the full eigen decomposition. The matrix was 2 NB by 2 NB, but we're going to pick the first to first A and B. Then reset XL. So the next vector approximation will be Z times the W vector of the smaller matrix. That's basically what it is. Okay. Right? So what's going on? Okay. Now this is talking about SD. SD, you have X and R. Now what about extended SD we talk about? Extended SD in the previous case, you look here, this R, you're gonna have X, Rx, which is C, which is A minus rho LB X. That gives you the residual. And the next one, and you stop at some point. So you can so basically at SD is the range of X and R together is a direct sum, not direct sum, of a lot of A and B Krylov subspace of order 2. And so how do we extend it? And naturally, same reason I was talking before. If it's a Krylov subspace order 2, we can make it order M because Y order 2. Yeah. So we're going to do extend each space order 2 to order M and sum together. All right. And now here for simplicity, we extend each Krylov subspace of order 2 to order M. Presumably, you can extend each Krylov subspace to different order. Now, those are just parameters. And then you, well, how do I know which one is which? How high the order should be? You don't. We don't. So just for simplicity, let's keep everybody M. And the one benefit of doing so is that somehow the sum of this Krylov subspace of order M can be written as a Krylov subspace of an operator R. This is a curl R, okay, calligraph R. Well, what is calligraph R stands for? Mean. Here, calligraph R here is mapping X of size n times nb to another matrix n times nb, which is given X is mapped to AX minus BX omega L. So it's a linear operator. It's not in the matrix form. So this curl R is not as a matrix form, but it's a linear operator. And you know this is linear. So then you define R to the i's power is basically composition of R to I minus 1. Then you apply once and apply I minus 1 more. Okay. So basically, this sum of Krylov subspace can be compactly written into a Krylov subspace of this operator R on XL. So just for easy presentation. The next is to you find the basis matrix of this Krylov subspace. Now, okay. How do you find the basis of this Krylov subspace? You basically doing a similar thing. Later, we're going to show the code similar by Arnoldi process. Okay. All right. Now, that's one idea of for making it go fast. From SD, we talk about from SD. There are two different ways to make the code go fast. Extended space, which I have implemented, you're going to implement, and then preconditioner, which I did. I show you. Now, then here we're going to do, we have the same idea. So you can do extended space, you can do preconditioner, right? So preconditioner, the idea is the same. So you take the residual, which now is the matrix you multiply by k. This k can be different from step to step, can be different from the eigenvalue which eigenvalue you are computing. So so this is more general by making k depend on the iteration index and depend on eigenvalue index. Just for generality. In the code that I on the web, my code is the simplest in the sense I make k independent of all those. The k is independent of iteration index, independent of eigenvalue index. Just to show the idea it actually works. The reason is that the creation of a preconditioner is not free. Usually costs a lot. So by using the constant preconditioner, although it makes the conversion rate a little bigger, but overall it may cost less in terms of computational time. So how do you get this preconditioner? The idea we talked about before is exactly the same. You can do for the jth eigenvalue, you do this k Lj almost equal to the inverse of that, all right? So basically, if we're going to do differently, and then you can implement by sometimes when you do that, this metric unlikely to be positive definite because you compute several eigenvalues together and the shift depends, and then you may have to use GMRes or MinRes in the code in the option that we talked about preconditioner. That the MinRes part is one of the options I haven't implemented. You're going to do that. Okay. All right. This is the first type. The second type is based on Golub and Ye's theorem. You're doing a LDL transpose decomposition, of course incomplete. And then the middle d is plus minus 1, and then you throw d away, that's Kij. The preconditioner is simply equal to LL prime. Okay. Yeah. And if put all idea together, there's no new idea together. Well, there's one new idea. Basically, the residual. You create a residual for each individual columns. That's the only new idea. The rest basically the same. So so you start with the initial. The whole iteration the key step will be right here. The preconditioner, whether going to be used one preconditioner or different, that's your decision, and you can make your choice depending on how difficult the preconditioner can be, how expensive it is. Then you have to compute the basis. All right. Once you have a basis, do a projection. It has a smaller matrix, you compute the eigenvalue. All right. And now in the end, you will have several approximations at one time. All right. Well, there's a lot of implementing issue that I already mentioned. Are you going to use the same preconditioner or different preconditioner for different steps, or different preconditioner to eigenvalue, each individual eigenvalue you're going to compute? In the code that on the web that I put it, I use one preconditioner for every iteration, for every eigenvalue, just to show the point. Okay. And another thing is the convergence. When you do a block version, you try to compute the first A and B eigenvalue together. The rate of convergence is different depending on the eigenvalue. You will see the first eigenvalue is quickly converged, then the second, then the third. So you might want, if you might have a tolerance we talked before, you might want to look at when the first eigenvalue are sufficiently accurate, you will say, I don't want to do any computation for that anymore. I'm just take that as where it is. So you're going to decide to do a deflation, right? So you can deflate anytime eigenvalue, usually converging order, the first, the second, third. Although there's no theory to guarantee that, but typically that's what happens. So when it happened, you're going to deflate them. So when you deflate them, there's typically people, the terminology called, you can lock that particular eigenvalue because it's already done, and then deflate it. And by doing that, the future iteration will no longer compute them, save work, right? So we will get the idea of deflation we already talked about. And another thing that once the first eigenvalue is locked, you might want to compute a new preconditioner. In the code I didn't, but you can do that. In the future, when you have a large eigenvalue computation, you might want to do that because it make it more efficient. That means that you can, once every eigenvalue converged, you might want to change a preconditioner to make it go faster. That's the first issue. Second issue, how do you compute the basis, right? You need to compute basis. There are a couple of options. First option that this is a sum of several Krylov subspace of one vector. So you can compute, for example, compute a basis for each Krylov subspace and put together. You can do that. But that has a problem. The different Krylov subspace might be close in certain way. So if you by computing each individual Krylov subspace, you get a basis put together, that final Z could be your condition. That's one. Second is if you're going to compute each individual, that's basically Bloch 2 operation, which means matrix vector operation. It's good, but it's not the best, right? The best would be using matrix operation. So here's the idea that suppose you do for the L step, your K is independent of eigenvalue. And then this Krylov subspace, as we talked about before, can be written as the Krylov subspace of the operator R, okay? Operator, the curl R, where this operator Rx is, we just talked about AX minus BX omega, and KRI operator is apply KR once, and that should be I minus 1. That can be I again. For example, the square would like that. And the reason to do that, you can, with the K the same, with M the same, you can basically doing a Arnoldi process. Okay. Only difference is anytime you do in the Arnoldi process, you do matrix vector or matrix block Arnoldi process. You do matrix the block vector operation. Here we're using the operator R. So this is the operator R. So this step is block matrix operation become the operator R. You apply operator every time the operator curl R does once. That's what here. Once you get a Y, which is operator times the previous vector, previous block vector, you do orthogonalization. This is a Gram-Schmidt orthogonalization. Now, once you get a Gram-Schmidt orthogonalization, this Y is supposedly to be orthogonal to be orthogonal, in this case, be orthogonal to all the previous Z blocks. And then the next one, you're just doing a QR, or use BQ, QR in B inner product, or you're doing a single vector modified Gram-Schmitz. Okay. Yeah. Okay. That will get you a basis. Once you get a basis, you do the projection, right? Now, there's a possibility because of Y after orthogonalization, this Y can have the rank maybe numerically low rank than the number of columns. So you're going to make a decision on that. So Zj plus 1 might have fewer columns than Y. That's because some of Y column is either 0 or depend on previous columns. Can happen. All right. The second issue is basic. The third issue will be, of course, the convergence. We talk about the convergence criteria. Okay, the residual, the normalized residual, if less than a tolerance, you give a tolerance like 10 to the minus 12, for example. You say, well, that's fine. This one is converged. Okay, and when it's converged, we need to lock it. How do we lock it? Basically, we're going to symbolic. There's a matrix D. In the code, we don't do a diagonal matrix. We do a array D to save the eigenvalue into D. And at the same time, we're going to save the corresponding vector as an eigenvector in U. And later, we need a B times U to do deflation. Remember that? Okay. So you're going to lock them. So every time there's a convergence, you're going to do that. You update D and update this boldface U. Then this NB, when you remember we have NB vectors to do the block version. If you have one convergence, NB is reduced by 1. All right. This is one option. The other option said, I don't want to make ND smaller. I just keep ND the same as to begin with. So then you have to append another vector to NB. Okay, so you already have so you already have convergence. So you take one out, then the number column is reduced by 1. But in order to maintain the same number, you append another vector. So that's what happened. And then your deflation. Deflation we just talked about. In all the code, we do deflation by the shift. Okay, so you update B, and then you put a shift right here. You update B times U into long skinny matrix, and then you pick a shift. This is something you have to decide what shift you're going to pick, and do all the iteration, right? Now, I do have, let's see, so if I look at this, this is a block SD with a shift. I test 3. Let's see what I don't remember it. I want to run. Maybe I want to run the last one. In the web page there's a version called sorry. Oh, well, I shouldn't do this. That's called block preconditioned steep descent with a shift. What's the X stand for? It would be expert version in the sense that if one converged, I increase the block. I maintain the block size always 4. So there's a block size called X4 of. Then I try to compute 10 eigenvalue. I try to compute 10. This code is more complicated. The preconditioner is still the same preconditioner. That in that sense, that's not that complicated. So every time there's an eigenvalue converge, I expand the vector, still maintain the block size 4, and if I run it, it would be well, let's take a look. Here it is 5. Yeah, how do you read this? How do you read this? So I have a block size 4. So you have a 4 line right here, red, blue, green, and other cyan maybe. So if very quickly you see that this line, blue line, get down to 10 to the minus 12. I think the relative error that I said was maybe 10 to the minus 10. So one step you get to this far. So this eigenvalue converged and it deflated and locked. And once it does, I append another column in. So if another column in, it will be will be right here. Would be the residual error going to be, because when the one you append in is not going to be very good, right? So the residual error going to be big, and that's why everybody jump up a little bit. This one already deducted, and you have a 4 right here. So even that's why it jumped right here. That's because once I dropped, I have a new 4 columns. It's a new 4 residual error. Their size is about from here, 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 here. Okay, so this is a plot defect that you link by the solid lines always. So then this 4 line keep on going down, right? I think a residual maybe 10 to the minus 8. I began to think, because some of them, oh, that's fine, 10. So it ended up here. So then quickly after a while, this eigenvalue converged, and then you appended another column. Then you have a new 4 residual error, which is bigger, and then one more. Then this is another convergence happened. So every at the bottom, every angle here is a place where one eigenvalue is determined to converge already. And if you log, it should be 10 of them. I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 eigenvalue. It stopped. The code, of course, when you think about this code, every time you converge, you need to update a lot of things. You update the D and the U. Then you need to update when the preconditioner is applied. Depending on the option you use, remember the Sherman-Morrison Woodbury formula. You have you need a precomputer. So try to update everything as much as possible, and not to repeat computing those that already been computed. Okay, so. Anyway, the code right there, you can play with it and look at inside to see what happens. Let's take about 10 minutes break. Now is 11:15, so 11:25. So far we talk about steep descent. There's a lot of ideas going to be applied later too. The idea of expanded space, idea of preconditioning. Those ideas are not limited to steep descent. So next topic we talk about conjugate gradient. We briefly talk about CG for linear system, which usually you learn from a numerical linear algebra class. They talk about that. One of the reference by Jean Golub and Vallon measure computation has a step-by-step derivation. It's very illuminating. You should read through it. And then another way to look at CG is in Jim Demo's book through connection with the Lanczos method for solving a linear system. That is less related to how CG was invented before, but Golub and Vallon's book has more close to the origin of the method. So then we talk about a conjugate gradient method, nonlinear conjugate gradient method, then naturally applied to the eigenvalue problem, AX equal lambda BX, because the minimization principle we talk about, okay? Then the rest are so-called more popular recently, so-called locally optimal variation, CG and its variations. And include extended idea that we talk about, steep descent, that apply here too, okay? Well, we talk about that, and let's just still refresh our memory. It transforms a linear system to a quadratic functional, and this is a convex function when A is SPD. The solution is unique, and the gradient of this function is the residual, same as the residual. And the steep descent will go with the residual, but here it introduces a set of direction, P, which is conjugated with respect to A, or you can say A orthogonal. So you start with you compute the initial residual. The first direction you try to minimize is, because it's just the beginning, is in the opposite direction of the residual. So every step you try to do, this is the line search, minimize the function value along line pi. P0 is a negative R0, and this alpha I is a minimum. Well, this is easy to do because this one line in the real case is simply a one variable calculus. You just take a derivative, you get alpha I. Then once you get alpha I, then this relation will directly tell you the residual relation. So this relation is simply a consequence of that, is by multiply. So if you have xi plus 1 equal to xi plus alpha I pi, you can always multiply a. Then you subtract b from both sides, and you get a residual equal to a residual I plus 1 equal residual I equal to alpha I API. So that's a simple consequence. Then the key part is this. The next direction is the negative residual plus beta I pi. How do you get to beta I? Beta I is basically is getting from to make sure P and Pi plus 1 Pi are A orthogonal. Okay. The way it does, it turns out there's a lot of optimality property for CG as a byproduct. That's very interesting. You can read the book. Beta I has several equivalent expression. Those are all the same in theory, but numerically may be different. One can prove they're same. There's only 3 here, but they are more than 5, 10 out there, maybe 10. Okay, that's a linear CG. Then linear CG then naturally this after CG was introduced in 1964, you get nonlinear CG. Before was phi x is quadratic. Now I say, why phi x has to be quadratic? We just do it, right? You know, one of our slogan in Nike say, just do it. Just do it. So replace residual by the gradient. Okay, everything Everything the same. The formula just formula exactly as before, except I. This is fine. This is fine, and then the residual, the direction is also defined by that way. You can do it, but you lost a lot of all the property in the linear CG case. So the linear CG case, even though pi are a orthogonal in the nearby in the neighbor vector, but in theory it is actually a orthogonal to all pi are all a orthogonal for different pi, and another optimum property is CG in the linear case compute the best optimal, the optimal solution in the first in the subspace spanned by first p. Okay, first few. The nonlinear CG that those properties no longer there. Okay, they're not there. Then you have come up with so-called that local, that based on assumption, based on the observation that in the nonlinear case you're still using same beta I except replace the residual by the gradient. And what are the reasons? Well, the reason is the residual is gradient. That's basically the only reason there. Other than that, is a little arbitrary. So in 1965, the Takahashi, he noticed that if you look at xi plus 2, that equal to xi plus 1 plus the scalar times the pi plus 1, then you plug pi plus 1 in, that's what you have. Then this is in the space of 3 vectors, right? Then you use the residual, the pi, then use xi plus 1 equal xi plus pi. Then the pi is basically can be replaced by xi. So xi plus 2 is in the space spanned by these 3 vectors. And his idea that let's find the next one that minimize the function in this space of dimension 3. And that's how local optimal come in. In the general optimization problem, even line search can be a problem. Can be difficult. Okay, if the phi is not friendly, the line search can take a while to do. You can even not solve the line search exactly. Then, not to mention, you now have to search the possible solution, best possible solution in the bigger space, even harder. It turns out this is for general optimization problem. Now for eigenvalue problem, it turns out if so long the dimension is not too big, the dimension is 5, 10, 100, even 200 is a search best possible solution is not a big deal. Okay, so that's why we see more use of so-called locally optimal in eigenvalue computation than in any general optimization problem. Okay, so this is for this ax equal lambda bx. That's a Rayleigh quotient, and we know lambda 1 is a minimum of rho x. So that's where the CG comes in to the picture. And the gradient can be computed. One of the homework does that. Also, I think we did that before. There's a factor here, but we're going to drop that factor because the direction matters more than actually a factor here that's kind of an inconvenience. So there's a line search problem. Most books say min. I like to use inf because might not be achievable. It's a small technicality. It's not particularly important from computational point of view. Maybe mathematically you do a little distinction. Doesn't make much impact in the computation. So we need to solve that. One of the ideas, if you look past paper and books, by, for example, the Computation of Linear Algebra, that Russian book by two Russian mathematicians. They actually, usually people do that by differentiation in the real case, when t is real. You take a derivative, you set everything, you set a 0, you figure out which one is what you want, you pick that one. Now, another a simpler way, maybe just to, if you have x and p, suppose this x and p linear independent, you can project the matrix and compute this 2 by 2. Take a little work. Get an eigenvalue, eigenvector, pick a smaller one because we're minimized. And then the possible argument, there are two choices, either infinity, that's why if there. If mu1 equals 0, if mu1 not 0, then you can have optimal t, that is. And then the y here, the y here, this y here is either x plus t optimal p or p, depending on t is optimal infinity or not, right? The CG in a simply possible way would be you just take the nonlinear CG, replace the gradient by Rx, and yet we are making another arbitrary decision here. In the linear CG, put all the gradient. Here we drop that. We simply drop that. Just put a gradient, put a residual there, right? So there are certain arbitrariness. This would be the first version of CG, simple enough, right? The only thing differ from SD. So if you look at this part, differ from SD is in the vector p here. Before was always the residual. Now is a p vector. P vector is always updated. Okay, updated here. Before you always put the residual all right there. Now it's updated. And then you have the BL, beta L. Which one you're going to pick? They perform similarly. There are differences. It's hard to say one is always better than the others. Then every time the next y approximation, and then we normalize it. Why do we normalize it? I don't know. Just we wanted to, maybe. So it's a kind of arbitrary, because in actual nonlinear optimization, you don't normalize that. Here we are able to do that because this x is supposed to converge to the eigenvectors. Only the direction matter. Eigenvector direction matters. If we multiply eigenvector by 2, it will still doesn't change anything. So now here we do normalization in the general. If it were a general optimization for a general problem, you wouldn't do that. Okay. All right. So there's a theorem, convergence theorem is, even though usually CG converge better, faster, without any preconditioner CG and a steep descent, you will see the CG converge noticeably faster most of the time. But yet, as convergent behavior is less well understood, here's one of the theorems called global convergence, proved by Yan in 1993. He proved that always, if you use this choice for beta L, okay, you choose this beta L. We do mention this another choice you might use in this formula, but his theorem says using this formula. And when you do that, he proved that this rho L is always converged to some eigenvalue. This is typically true because the rho L is going to be going down, bounded from below by the calculus that the monotone sequence is going to converge to eigenvalue. And there's a subsequence. Okay, here's a difference from SD. In the SD case, this A minus lambda had to be XL for all the vector, not just a subsequence. This is the difference from SD. It's only the subsequence, the residual of the subsequence goes to 0, not the whole sequence, okay? And this XLI, the subsequence, going to converge to the eigenvector, corresponding eigenvector. Now there's a special case that if this lambda had to be the first eigenvalue, the smallest eigenvalue, then you can prove this the whole sequence converges to 0, the residual converges to 0. Only a matter of proof. This second part wasn't isn't in the theorem in a paper by Yan in 1993. At least I didn't see it appear anywhere. Looks new for me, but it's not that difficult anyway. So we just mentioned that. So we mentioned first 2, and although in the SD case, such a theorem was when we proved such a theorem it didn't take much effort. Actually, 1 slide we prove it. It turns out for the CG case to prove this first part, you may have to take 5 slides. It's much more complicated. I'm not going to reproduce it here. Yes?
So that's why in the preceding parts, we always try to approximate lambda 1 by rho L, because we know how the sequences converge.
Usually it goes to lambda 1. It's hard not to go to lambda 1. There are a couple. The one reason is even though in theory, if you start with a vector that's deficient in the first eigenvector, in the standard eigenvalue problem, in theory you can never converge that particular eigenvector if you start with a deficient. Generalized eigenvalue is different. Even that rounding error, this is a place where rounding error help you. That even though you unfortunately start with a vector that deficient in the direction of the eigenvector you're looking for, somehow in this case, in rounding error comes to help you, push you towards the first eigenvector. Well, it could destroy you too. You might not. You might do that on purpose to begin with. I don't want to compute the first eigenvector, yet rounding error going to push you toward the direction. Okay, depending on how do you look at it. So even though here they convert to some eigenvalue, more often than not, is the first eigenvalue. Okay, all right. The rate of convergence of CG is, although people talk about how fast it converges, and mostly heuristic. There's no rigorous proof as far as I can see. That's why I didn't put any theorem about rate of convergence for CG in this lecture, because none of them that satisfies me. So, all right. Then you talk about preconditioning. Same idea. Preconditioning. You look at it before that. We have a original problem. Then supposedly looks like as CD, SD, we're going to transform the problem by L inverse from right, L inverse H from left. And let's call this a new pencil with a tilde. So I'm put this transform pencil, everything associated with transform pencil, put a tilde onto it. All right. For example, the eigenvector for the transform one called x tilde. So x tilde and x is related by x tilde equal to Lx. Okay. So there's 2 set of notation parallel, one with tilde, one without. So then you have rho tilde x tilde. Rho tilde will be the Rayleigh quotient for the tilde matrix. So by definition it will be that, right? Then you're using the relation x tilde equal x. you found out the rule doesn't change. That's expected because the transformation doesn't change the eigenvalue. Then the residual was with the total for the total matrix. Then by definition, this is what you have. Then you use x total equal to Lx. You take L out. So the residual in the total case, the result without total case is related by a matrix multiplication from the right, L inverse H. Now, key step for CG, for the total, so this is a total case, key step of CG. So you do the optimal line search, and that could be if. Then you update the X eigenvector, and the residual, you compute the residual, then you update the next direction. Now, perform a simple substitution. X total equal to Lx, doing that. R total equal to L inverse HR. You plug in, and you discover alpha L total is become XL plus alpha total here, and times L inverse PL total. X is updated like that. Residual R is, well, that's a residual R. Then the P total, you multiply L inverse from the left, and you redefine PL to be L inverse PL total. So you discover that the PL plus 1 equal to K times the negative R residual and beta. So the formula is the same as before, okay, right? So this is for the one without total, and you instead of working with total, you're going to update the P. So that give you the CG. Now let's look at the difference here compared to the no preconditioner. So here, before was P0 equal to negative R0. Now you put a negative K. You apply K, the preconditioner, to it. Okay. So the residual is applied by K. Then you look at this is a line search as before. Then you look at this is different than without preconditioner. So before was there's no K here, just simply negative RL plus 1. Now you apply K to it. So so the idea is so everything just a little adjustment. The only thing here now beta here is different. Before was no K here. Now just put K in between. It's an inner product with red K. So because of this, your K has to be positive definite. Okay, and different from SD. If you're going to do CG as is, you're going to be K to be positive definite. Now. Convergence we mentioned before. So I think it should be preconditioner. So how do you do a preconditioner? We're going to do back to the SD to look for motivation. In the SD case, one of them will be doing an incomplete decomposition. You make K equal to LH L inverse, right? Another is in LD case that if A minus sigma B is positive definite, you can just use in the inverse of that. All right, then you can do a CG. So the conversion rate that I mentioned before, that mostly are non-rigorous. People just say it should converge like that. Usually better than that. None of them are very well rigorously proven. So you can look at convergence rate from SD to draw a conclusion that usually that's much better than that. Okay. Then talk about global convergence that we just mentioned. This theorem, this theorem will be still remain for the preconditioner, because the preconditioner basically the CG on that matrix. So that's still true. All right. I'm not particularly happy with the state of art of convergent theory of CG. So there's a lot of work can be done. I just don't know where to start. It seems to be a difficult problem to do. Now, I mentioned before. Look at that from linear CG to CG, we already made some kind of arbitrary choices, right? In particular, there's beta choices. Now, this arbitrary is not totally arbitrary, but there's something that's unjustified. It's hard to say you have to do this way. In the eigenvalue computation, we have additional arbitrariness that we did. First of all, we dropped this factor 2 over x h b x. Why can we drop that? Anything you drop, you're going to have an effect. What is an effect? We don't know. Nobody knows. So that's one. Another that we normalize the XL. Every step we do that by B norm. Of course, you can use other norm as well. It seems it has an effect, but not too much. But you know, the overall convergent behavior basically the same. So this the second one is the second choice doesn't show up in the general CG for a nonlinear optimization problem. Okay, but we just do that. So you see the arbitrariness is right there. And it still works. It's a magic, kind of magic in that sense. It still works. And you can download the code and make some of arbitrary choices, not too drastic. And you will see you convert. You put a factor 2 there, you put a factor half, factor a third. The curves still go down in a similar way. All right, so it's not easy to explain those choices, and nobody knew how. So it's not clear. Now, and we talk about then maybe we should get rid of the arbitrariness to go take another approach. This is so-called locally optimal CG comes in. Instead, the idea is, we talk about that you get rid of all the p vectors altogether. This x L plus 1 approximation by finding it's computed from the by minimize the Rayleigh quotient on the space of dimension 3. The current, which is XL, the previous one XL minus 1, and the current residual. So it's going to be a three vector span space, okay, in the dimension 3. Like I mentioned that in general, locally optimal CG is difficult for a general nonlinear optimization problem, because even line search can be difficult. But for eigenvalue problem, so long the dimension is not big, a couple of hundred is not a problem. You know, maybe even 500. Nowadays, if you run MATLAB, if you test it for a matrix of 1,000 by 1,000, it doesn't take long to compute everything. But 1,000 is probably big. So dimension 3, nobody cared that much. It's going to be done fast. Okay, so now if you look here, what's this differ from previous one? It looks a lot more like SD, right? It's actually more like SD than CG. In the SD case, you just don't have that, XL minus 1, okay? If you look at this compared to SD, it's only difference that you put one vector here in. SD case always dimension 2. Now it possibly is a dimension 3, but usually dimension 3 because you put the current vector, the previous vector, and current residual direction, 3. Okay, that's all to it. So your projected problem, this projected problem is either 2 by 2 to begin with, because in the first iteration, or 3 by 3. All right. Now, as is, they may have a problem. It's not too much a problem as I run. The one thing you observe here, look at this here, that it is hope, and of course we hope that, otherwise we wouldn't be doing that, that this XL going to convert to the eigenvector. So it's conceivable as your iteration move further, this XL and XL minus 1 should be almost the same, linearly dependent. One, if you look at one, the other maybe just the scalar multiply, because they're supposed to converge to the same direction, right? So there's a possibility that when you do compute the basis of these three-dimensional spaces, and you can suffer catastrophic cancellation, because when you orthogonize, say, XL minus 1 against XL, because they are almost scalar multiply one another, then you simply subtract the whole thing out, leave out the everything is a round off, or close to. Okay, so that's one of a thing. It can be, turns out it can be addressed. All right. So how do we address that? So if we can get L minus 1 by sum of the difference between XL. So if we can someone can compute the difference between XL and XI minus 1 directly, rather than compute the two vector and subtract, right? If you compute the difference directly, that means you're going to get the difference accurately. So we call it YL. Then the span of these three vectors is going to be the same as XL, YL, RL. Let's see how we do that. So let's suppose we at this point we have current place, we do have XL, YL, RL. Then we need to update, we wanted to compute the next one. Now, to next one, you're going to, well, let's take a look. This is a Z vector currently. If you do a modified Gram-Schmitz, so Z1 is almost XL, right? Then Y is in the next vector. This Y is the next approximation. So let's look here. So this Y equal to the Z vector times the eigenvector, and Z was a basis. So if we're doing a Gram-Schmitz, basically QR decomposition, then Z1 is the first vector in the list. All right. So Y, the next eigenvector computed would be Z times V equals this, and because Z1 equals XL, so you replace Z1 by XL. Then Y minus mu1 XL would be the difference, right? So this Y minus mu1 XL would be the difference, which is going to be the last two, right? So Y minus mu1 XL would be mu2 Z2 plus mu3 Z3. And let's see what that is. that would be equal to this y equal to the next approximation normalized, right? So so y normalized get next. So so we put it right here. So let's see. Y equal to xl times y norm. So that should be y, not x hat. That's a typo. Minus mu 1 xl equal to somehow is a difference between the current and the previous one. So this, if you do, but this can be computed directly. Now, how do we compute this this yl plus 1 directly? You simply take a z vector multiplied by v such that v first entry set to 0. See, because we're computing mu 2 z2 plus mu 3 z3. So if you set mu 1 equals 0, you got that. Okay. So there's a yl plus 1 equals z times v hat. V hat is a v set the first component to 0. So this way you compute the difference directly would suffer less from the cancellation. Okay, that's the one of the we need to do. How about convergence? Now it converges a lot easier, much better than Young theorem. The reason is that for locally optimal CG, the residual R is in the search space. So the gradient, the global convergence versus SD method apply here. Okay. So this is the same as SD. But in general, for CG, PCG, there's only the subsequence. Okay, that's a big difference. The inclusion of the residual RL makes all the difference in the proof. Okay. Now, how do we improve locally optimal CG? Now you know the idea. Import all the idea you learn from SD. Okay, the first include preconditioner. Okay, and now it becomes a universal idea. If it fails, preconditioning. So preconditioning is a keyword. So it works every single time, huh? If you have the right one. So that's one. The other is CG is actually we just talked about is differ from, well, how to differ from SD is basically add the previous vector right there. Okay, that's all the difference. So then plus the Krylov subspace of dimension 2. So you make it dimension m. Now make everything trivial. Now you see the idea. That's not a whole lot of new idea, but it works. The second option. The third, use a block. Okay. Now I suppose you know every trick that I know now. So 3 things, nothing more. Preconditioner, extend space, block. Okay. Then you can pick a name. You just put the words in. I don't want to bother to read all of them, right? Local optimal, block, precondition. I just put the word in certain order you like. All right. Locally optimal CG, locally optimal block preconditioner CG, and you see the code how different. Look at that compared to SD will be just that. Okay, you add the spacing in the SD by the previous vector, previous approximation. That's all to it. But increased implementation is going to be different. Theoretically, in form doesn't do a whole lot change, but how do you compute this basis can be a problem, which you will do when you look at take my code and modify, assuming you're going to do that, right? All right. Another thing is, moments ago we talked about that, so here's the xl minus 1. So we might want to replace it by some difference, okay, yl, as we just talked about. So as we just talked about it, we don't want to put xl minus 1 there, but just compute the difference between xl minus 1. So the same thing, implementation-wise, you have that. So yl. Then you look at then you look at what's the difference. Same as before. The next approximation was z times w. W is the eigenvector. Now, so w is right here. So the w is the eigenvector. Now, yl plus 1 is the next one, also times the so-called w hat. What's the w hat? W hat is w. You take the first n, b rows, 0. You zero that part. Before was we zero the first entry of v vector. Okay, remember that? We're using v hat. V hat is different from v by put the first entry of v 0. Here, you're going to put the first n, b rows 0. And when you do that, this will be the difference. And when you then, instead of xl minus 1, you put the difference right there. That will make it more numerically stable. All right. So then again, we need to compute this basis. How do we do that? We're going to take the simple case that all the preconditions are the same, and the first part of a space, the sum of this space is become a Krylov subspace of an operator R. So you can do an Arnoldi type. So you can do the Arnoldi type for the first part. So this first part you can do Arnoldi. We talked about that before. Then you appended a y to it. How do you append a y to it? Suppose you already have a basis for the first part, and you be orthogonize y against z1, z2, zm that computed first part, and then basically the Gram-Schmitz. All right. Then you once you get B orthogonized, you do the QR like thing. You get the next appended to it, so you get a big Z and do the projection. Okay. Okay. Reference. So this the list. This is a reference for several convergence results. None of them are simple enough or clear enough or convincing enough that I like to put here. So, but I list here that you can read it. Maybe some of you are going to come up with a better idea. Okay. All right. So let me just show you some of the routine. Then we're going to stop here for the day. So, all right. So we have, if you look at this, if you download the code that's called test CG, a lot of options. There's more options than you can bear, probably. The CG, well, let's look at one case called CG. Would be the same place. Let's see. This one we saw before. If we do CG1. Enter. Whoops. This is just if I do a plan CG. This is this CG, is it? Yeah, it's just a CG. And now, if you recall the previous picture, when we do SD, the first eigenvalue didn't converge that far. The rest are even worse. The first eigenvalue value converge, the residual does go down to 10 to the minus 6, if you recall. Then the rest is just doesn't go down that much. But CG here, you see the first one quickly go to 100 iteration go to 10 to the minus 9, I suppose. Is something like 10 to the minus 10, maybe 10 to the minus 10. Then the next three, with the deflation that we talk about, shift deflation, and just do it that way. So then I have the final routine with the preconditioner, the same preconditioner we talked about before. Let me just show you, just outline there. So the same preconditioner that you see, this is the exactly same thing. One of the options that when A minus sigma B is indefinite, I haven't implemented it. So obviously more work has to be done. And there's another so-called expert routine I can run. So X locally optimal CG, preconditioner CGS. I actually have two, one with preconditioner, one without. So it will perform similarly. So there are two cases, one without preconditioner, 7. Let's see that. Then the last one with preconditioner going to be faster. So we can see one of them. Let's see. 7. Let's put 7 in. Enter. This has no preconditioner. So in the SD case, without preconditioner, is not much convergence going on. If you want to get very fast, very small tolerance, and it won't do you any good. This is again with block size 4. I asked for 10 eigenvalue. It didn't finish at 10 eigenvalue, but this is without preconditioner. So even without preconditioner, it goes this well. The residual is this 10 to the minus 13. See how many eigenvalue converged? Actually, 1, 2, 3, 4, 5, 6, 7, maybe 8. If I do one more, to the last one is even more complicated. This with preconditioner. Yeah, the curve a lot better as everything shifted down faster. Now, one thing you notice moments ago was up to 500. Here is maybe 38, 39. So the power of preconditioner. Okay. Well, I guess everybody hungry. I'll stop here.